Okay, thank you very much, Mr. Chairman, for the welcome. And it's a pleasure to be here in Savannah, my first time. So, I shall be talking about principles of PET and SPECT. And first of all, I'd just like to cover the learning outcomes for this lecture. At the end of it, hopefully you'll be able to explain the tracer principle and its importance in PET and SPECT molecular imaging, how radiation emitted from the body is detected externally using SPECT and PET instrumentation, and the key principles in forming a reconstructed image of the tracer distribution in the body. So nuclear imaging with PET and SPECT is based on the tracer principle, which was first conceived by George de Hevesy. And in the tracer principle, we have an entity called a radiotracer, which is a chemical compound in which one or more atoms have been replaced by atoms of a radioisotope that can be subsequently detected by virtue of their radioactive decay. For imaging applications, the radiotracer, or often called radiopharmaceutical, provides a means to construct an image showing the way in which the radioactive compound and its reaction products are distributed around the organism. And this can also represent the behavior of related non-radioactive counterparts. For example, in PET we often use FDG, fluorodeoxyglucose, which is an analog of glucose, to study glucose metabolism. So now I'll just cover some key features of SPECT and PET. In PET, radioisotopes are cyclotron produced. Radioisotopes typically have short half-lives measured in minutes or hours. And each nuclear decay releases 2 gamma rays, which therefore requires coincident detection. And we use electronic collimation, which has very good detection efficiency. And PET scanners are generally constructed as stationary ring detectors. SPECT, on the other hand, radioisotopes may be reactor, generator, or cyclotron produced. Radioisotopes typically have longer half-lives in the region of hours or days. They release 1 gamma ray per nuclear decay, hence the name single photon emission computed tomography. And they require physical collimation, which gives us poor detection efficiency. And usually SPECT cameras have rotating detectors. Now here's a table of commonly used nuclear reactions to produce radioisotopes used in PET and SPECT. In the brownish area are some nuclear reactions to produce common PET radioisotopes. So the first one, sorry, wrong button. The first one here is production of fluorine-18 from oxygen-18 as a target material by bombarding the oxygen with a proton, releasing a neutron and changing the element into fluorine-18 with a half-life of 109 minutes. So this is called a PN reaction. The target material in the next one for nitrogen-13 is oxygen-16, and it's bombarded with a proton, releasing an alpha particle to produce nitrogen-13 with a half-life of 10 minutes. I won't go through all of these reactions in the interests of time. For SPECT, the most commonly used radioisotope is technetium-99m with a 6-hour half-life, and it's produced from the decay of molybdenum-99 in a generator, and that molybdenum-99 is produced in a nuclear reactor from molybdenum-98 by an N-gamma reaction. Okay, so those are the most common radioisotopes in PET and SPECT. Now in PET, the mechanism of detection is a little bit indirect. We have a nucleus of a positron-emitting element. Here is carbon-11. It emits a positron, which is equivalent to an electron but positively charged. And in doing so, it decays to boron-11. The positron then travels a short distance in tissue, losing energy along the way until it encounters an electron, at which point the electron and the positron combine to form positronium, which then promptly annihilates, releasing two gamma rays in opposite direction, each with energy 511 keV. And that 511 keV is no accident. It's a product of Einstein's equation E equals mc squared, and 511 keV is the energy equivalent of the mass of an electron. Now, the most common type of detector for detecting gamma rays in both SPECT and PET is the scintillation detector. It comprises three components: a scintillator, a light guide, and a photodetector. The scintillator is a special material which produces light when it interacts with an incoming photon, so-called scintillation. So here is an incoming photon. It strikes the scintillating material, which is typically a crystal of some sort, releasing light photons, which then travel out through the transparent crystal, through the light guide, which couples the scintillator to the photomultiplier tube, and into the photocathode of a photomultiplier tube, which is serving as our photodetector in this case. That releases some electrons by virtue of the photoelectric effect, and we have initially a weak signal, which is then amplified up by passing through a series of diodes, which accelerate the electrons until they reach the anode, and we have a larger signal, which is useful electronically for further processing. Now, the next talk will probably cover the subject of scintillators in some depth, so I'll just very quickly cover some of the basic elements of scintillators. We'll look first at sodium iodide doped with thallium, which is by far the most common scintillating material used in SPECT. And in terms of the properties of scintillating materials, the things that we would like to have are high density to ensure that the incident photons are absorbed in the crystal and don't pass straight through it. This is coupled with the effective atomic number, which again increases the probability of interaction with the crystal. We'd like both of these to be as high as possible. The light yield is important because we want to have a nice strong signal out of the photodetector. This is especially important for good energy resolution. And also we'd like to have a fast time constant for the decay of the light signal to enable high count rate studies. So that's sodium iodide. If we compare that now with some of the more common PET scintillating materials, and particularly the most common, LSO, you can see that if we contrast these two, LSO has much higher density, which is good for stopping the high energy 511 keV photons in PET. In SPECT, by the way, we're normally dealing with much lower energy photons of around 140 keV. And we have good light yield comparable to sodium iodide, and we have much shorter decay constant, which means that this material is well suited to high count rate studies. Now let's look at some of the instrumentation. Here is a SPECT camera, a typical SPECT camera. This is a dual head SPECT camera. It consists of two gamma cameras mounted on a gantry that can rotate them around the patient who's lying on a couch like this one here. So the couch is inserted between the two detectors and they rotate around the patient. Being a gamma camera, each of these detectors operates as shown here. So here is a cross-section through the gamma camera. You can see that there's a lead collimator in front of the scintillator crystal, which is a monolithic crystal, and then coupled to that crystal is an array of photomultiplier tubes. The purpose of the collimator is to reject any photons that are not traveling in the desired direction. In this case, we've got a parallel hole collimator, so we're only wanting to see photons which are traveling normal to the detector. Any others will be absorbed in the collimator. So when such a gamma ray comes in, it interacts with the crystal, releases light, and if we look on a top view at the bottom here, you can see that this light release is seen by many photomultiplier tubes surrounding that scintillation. And the intensity with which all of the photomultiplier tubes see that light can be decoded into the position in X and Y of the scintillation. This is so-called angle logic. In PET, there is no need for a physical collimator because we have electronic collimation. We have a complete ring of detectors, and when an annihilation event occurs, it releases these two photons which are detected within a short space of time of each other, and that time is called a coincidence timing window, typically about 6 nanoseconds in length. And when the system detects this coincident event on two sides of the ring, we're able to infer that there was an annihilation event somewhere along the line between those two detectors. So we get the direction information of the travel of these gamma rays not from a collimator, but just by knowing which detectors were involved in the coincidence. In practice, the ring of detectors is made up of a series of blocks. So each block consists of a block of crystal material with cuts in it part the way through, and an array of photomultiplier tubes. And here's a picture on the right of an actual block detector, which has been cut into an 8x8 array of detector elements, so 8 rows and 8 columns. And the 4 photomultiplier tubes coupled to the back of it are able to use angle logic to determine which of those 64 detector elements was involved in the coincidence. So now, to cover the next section of this talk, it's about tomographic reconstruction. So I've described very briefly how we obtain information about how we detect events in PET and SPECT, and from those events we can construct projection views from multiple angles around the patient. In all tomographic medical imaging techniques, CT, PET and SPECT, we acquire information about the makeup of the object we're imaging along ray paths, lines of sight. So in CT, we obtain information about the attenuation along a ray path between an X-ray source and a detector. In PET, as I've described, we can build up information about the number of decay events along any line of sight between two detectors, which incidentally is called a line of response. And similarly in SPECT, over a period of time, a SPECT camera will acquire at each projection angle information about the amount of radioactivity along ray paths parallel to this one through the object. So don't worry about the equations I've shown here. What we're doing in all cases is acquiring line integrals of the radioactivity distribution along all possible lines of sight that we are able to image with the detection system. And it's those line integrals that are then used in the reconstruction. The earliest attempts at tomographic reconstruction in medical imaging employed a method called simple back projection. And to illustrate that, if you look at the left panel here, what I've shown here is simple back projection using just two projection views. Now this might be PET or it might be SPECT. So we've got a detector positioned up here at the top that has taken a projection view looking down, and we've taken another projection view at right angles to that from the side. Now, over a period of time, the detector will accumulate information about the number of counts that have been detected across the surface of the detector. In simple back projection, all it has done is that the measured signal is spread out evenly across the imaging plane. So whatever signal was acquired at this position or any position across the detector is smeared out equally all the way across the imaging plane. And you can see that when this is done for just two angles, we can get some information about where the unknown activity distribution is located, because we've got reinforcement in these dark areas. It gives us a sense of where the radioactivity is located. And if we have the luxury of more angles than two, we can reconstruct something that gives us some useful information about the location of the radioactivity in the object. But with simple back projection, there is a problem, and that's blurring. And this blurring is described by a 1 over r function in the spatial domain. If we were to take a horizontal profile, or any profile actually through the center of this image, say along this line here, and plot it, even for a perfect point source, we would not see a perfect point source. We would see this function which is described by 1 over the magnitude of r. And that's a problem with simple back projection. This is equivalent in frequency space to 1 over f, a 1 over f function. And to compensate for this problem, the question posed is, what type of function would we need to multiply 1 over f by to result in a perfect reconstruction of a point source, that is a delta function? And the answer is that we would need to multiply by a ramp filter. So a ramp filter, shown here as a dotted line, would compensate for this function perfectly mathematically. And it's the ramp filter that is used in a reconstruction method that you may have heard of called filtered back projection. In filtered back projection, the projection data are filtered using a ramp filter prior to being back projected. And here is the result of now applying the simple back projection method that we saw before, but this time to projections that have been filtered with a ramp filter. And you can see that now we have a much clearer representation of the radioactivity distribution, and we don't have erroneous indication of a background activity level that's due to the blurring, that would be due to the blurring of the unfiltered back projection method. And filter back projection is used extensively in CT with the ramp filter and gives very good results. So just showing that again, here we have the information required to reconstruct one slice of an object. This is called a Synogram. It's a compact way of representing all the information needed to reconstruct a single slice. It's an image that has the same number of rows as we have projection views. So each row of this matrix is a different projection angle. And across the matrix we have the information acquired at one projection angle by the detector. So the first step in filterback projection is to apply a ramp filter to this raw Synogram. Here is the ramp filtered Synogram. And then we proceed to reconstruct progressively using the available projection angles. And you can see that as we increase the number of projection angles, we eventually, when we've used them all, achieve a reconstruction that looks quite reasonable. This is a brain reconstruction. However, there is a problem with filterback projection. It works very well when there is no noise or very low noise, as in CT. But real projections in PET and SPECT contain noise. And therefore, filterback projection produces a noisy image with streaks and artifacts if we have a lot of noise. And another way to reconstruct the data that overcomes that problem to some extent is iterative reconstruction. And I'm going to describe how the iterative reconstruction works. We start with our measured projections as before. This is our Synogram. And the first step in an iterative reconstruction approach is to make an assumption about the actual object radioactivity distribution. So we assume a uniform object, and then using our knowledge of the imaging system, we simulate the detection process by performing a forward projection, and we produce from that uniform object the projections that we would obtain from it, or we would expect to obtain from it. And the next step is to compare those predicted projections with the measured ones by taking their ratio, and then we update the estimate of the object. And you can see that now we have something that's no longer uniform. And we again forward project that updated reconstruction and obtain now an updated set of projections. Again, we compare them with the measured projections, and I think you can see what's happening as we proceed around this iterative loop. We progressively improve the estimate of the object that we're trying to reconstruct, and at the same time, by forward projecting, we obtain estimated projections that begin to more closely resemble the measured ones, until we ultimately get as close as we possibly can to the measured projections, at which time we hopefully stop the iteration around about that time. So once we have got the estimated projections corresponding to the measured ones, we can say that, well, this estimate of the reconstruction corresponds to the actual radioactivity distribution. Now, mathematically, we can express this algorithm, this equation. On the left, we have, this is the update step, so this is the new value of a voxel. Here is the previous value of an image voxel. And the equation involves a matrix, which represents the probability of an image voxel J contributing to a Synogram bin I for every possible combination. And also the Synogram counts measured in bin I. These are the measured projections. And this Y hat I is the estimated projections that are obtained by forward projection. So this method produces a non-negative solution. It only involves projections and back projections, so they're easy forward operations. It's guaranteed to increase the log likelihood of the estimated image given the measured projections. with increasing iterations, but it's computationally demanding, and I'll show in a moment how that can be overcome. Just quickly to illustrate again that as we perform this process and proceed through the iterations, the log likelihood increases continuously. So MLEM, if you compare it to filterback projection, here at the top panel we have filterback projection images for a relatively noisy study. Here are the MLEM reconstructions, or slices, and you can see they look much more pleasing than filterback projection. Another advantage of MLEM is that it allows modeling of the physics. So we can, for example, model physical effects like blurring in the detection system itself. So here are some images reconstructed without any resolution modeling, assuming simple ray tracing and that the system has effectively perfect resolution. But if we build into the forward projection model a physical effect that we know is actually going on, like blurring of the system, then we can actually implement a correction for that. So here in the lower panel are images obtained where the resolution of the system has been incorporated in the forward projection model. And we have an improvement in the resolution of the system. And the same approach can be used to correct for things like attenuation and motion. If we make the A matrix that I showed before time dependent, we can correct for motion as well. So it's able to do a lot of things that filterback projection can't do. To accelerate MLEM, the phenomenon of ordered subsets was discovered in the 1990s, or I should say rediscovered. Like everything, it had been discovered previously by someone called Tanaka. Ordered subsets achieves acceleration relative to standard MLEM by operating on subsets of the projections rather than all of the projections at once. So in conventional MLEM, at each update step, computations have to be done on all of the available projection data. In ordered subsets, this is only performed for a subset, for example, 2 or 4 projections out of the total set. So here's an example where the subset consists of 2 projections at right angles, and as each of these sub-iterations is performed using the same algorithm but less data, the reconstruction gradually improves until at the end of processing all of the projections once, we have this reconstruction here. So in this case there were 80 projection angles, and we used a subset size of 2. So that meant after 40 of these sub-iterations we had treated all of the angles once and done the same amount of processing as a single iteration of conventional MLEM. But the interesting thing is that we have progressed 40 times as far towards the eventual solution in doing that as conventional EM. So the acceleration factor is 40 times in this case. And that's what has made the MLEM algorithm much more amenable to clinical use. So I'm running out of time already. Just like to talk quickly about photo interactions in tissue. The 2 main effects that we need to consider for quantitation in PET and SPECT are the photoelectric effect and Compton scattering. In the photoelectric effect, the photon is completely absorbed. In Compton scattering, the photon interacts with an outer shell electron. In doing so, it loses some energy and it changes direction. Both of these effects can give rise to quantitative errors unless they are compensated. So they give rise to attenuation, which is a diminution of the signal due to absorption within the patient. So in SPECT, if we have a source of activity here and a gamma ray traveling out along this white line, the count rate on that line, C, will be related to the emission count rate internally by this equation, where mu is the linear attenuation coefficient and A is the distance or the path length through the body. In PET, there is a major difference because we need to detect 2 photons to get a coincidence event. And in this case, a photon must traverse the equivalent of the full depth of the patient to be detected. So now our equation has A plus B for the distance of the length of the path. And the effect of that is that attenuation correction factors are lower in SPECT than in PET. In SPECT, they're typically 5 to 10 in the chest for technetium 99M, but in PET, they are of the order of 20 to 50 in the chest. There's also a problem of scatter. Now, scatter is a result of the Compton scatter I referred to, and it results in the deposition of activity outside the body in PET. So here's the scattered event, which we have a photon traveling this direction initially, then it interacts, scatters and changes direction, and that gives rise to the assumption of a line of response along this line, which is not useful information. And scatter can also occur in SPECT. But differences between them are that in SPECT, scattered and unscattered LORs cannot be formed outside the body, whereas they can in PET. And this makes a difference to the ways in which we can counteract scatter. So just showing the effect of scatter and attenuation correction. So here on the left, these 2 panels are showing reconstructed images without attenuation and scatter correction. Without attenuation correction, we have a reduction in the apparent activity deep within the patient. If you compare that with the corresponding area with attenuation correction, it's much lower over here, and scatter correction cleans up the image considerably. And finally, just a reminder that both SPECT and PET can be used for dynamic acquisition, so we can acquire images over a series of images over time to get the time evolution of uptake in tissue. This is an example actually of a dynamic SPECT study in a baboon that was used to show upregulation of acetylcholine nicotinic receptors in a baboon, and also to produce useful parametric images of the volume of distribution. The same things can be done in PET. Okay, so just in summary, PET and SPECT are based on the tracer principle, whereby radiopharmaceuticals are administered at minute concentrations such that they don't perturb the system. The radioactive emissions are recorded by very sensitive radiation detectors surrounding the subject. The recorded emissions form line integrals representing the accumulated activity along lines passing through the subject. These line integrals are reconstructed into tomographic images using an iterative or FBP algorithm. Mlem is slower than FBP but can be accelerated using OSEM, and it can also incorporate detailed physical models of the imaging process. And PET and SPECT images are inherently quantitative when appropriate corrections for photon attenuation and scattering are performed. Thank you. think I've